What's up, guys? This should be a relatively quick one. What we're going to be talking about is vertical asymptotes. So a function has a vertical asymptote at x values for which it is undefined. So remember, that's dividing by 0. And near which the values become very large positive or very large negative numbers. So let me show you what that looks like with this first example right here. First, let's actually find the vertical asymptote. So determine the vertical asymptote of the following functions. So for the vertical asymptote exists when we are undefined. So I cannot be equal to 0 here. So what that means is x cannot be equal to -3. It's just not possible. So let me pull up Desmos real quick and show you what the graph looks like. Desmos, that's not the right one. Start graphing. So y equals, that's minus 1 over x plus 3. 1 divided by x plus 3. So look at it. At -3. Here, let me make another line. X equals -3. All right, so that's the value that I cannot have. So what that is, and usually you'll see it as a dashed line. Dashed line, that's so pretty. As we go out forever and ever and ever and ever and ever. So following our function, I know we're like super way out there. But notice, it says -3, but it's staying at -3. That is just saying it's getting so incredibly close to -3 that the graph actually thinks it is -3. And that could be on my line too. I can't tell if I'm on the red or the blue there. But if I follow the red up, notice it's getting really close. Come on, computer. I believe in you. You can do it. It's working hard because it's uploading another video. Oh, there we go. I don't know what's happening. But as we go up forever, we're -2.9 something, and then it jumps down, and it's getting closer to -3 there. And notice the red stays all the way out here. So if I take away this blue function, the red is still there, but it's essentially getting really close to that blue function, which is our vertical asymptote. So let's take it back to that. So this is essentially our rational function, and we're getting closer and closer to -3. It's going very large in the negative direction here, and very large in the positive direction there for our y values. That's what we're talking about when we say the very large stuff. All right, so that's it. That's essentially what vertical asymptotes are used for. They're used for graphing, as well as our zeros, but we'll get to that in the next video. All right, so for the next vertical asymptote, it's when 5x squared cannot be equal to 0. So if I solve for x, if I divide by 5, then that would give me x squared cannot be 0. If I take the square root, x cannot be plus or minus 0, which is just 0. So there would be the vertical asymptote for that one, vertical asymptote. Next one, 3x minus 5 cannot be equal to 0. So if I add the 5, divide by 3, x cannot be 5 over 3. That is our vertical asymptote. Oh, we can have more than one as well. So this graph looks kind of cool. Let me pull up Desmos and I'll show you what this one looks like as well. We'll do that after we solve it. But x times x minus 1 cannot be equal to 0. Essentially, this is a quadratic function that's already been factored. If it hasn't been factored, then you can factor it to find your solutions or your zeros or your, in this case, vertical asymptotes. But it's where we are equaling to 0. Oh, I got the space monkey back there. Space monkey. I don't know if you've seen the space monkey. Space monkey. Ah! What's going on? All right. Sorry. I just had to show you the space monkey. So what this means, x cannot be 0 and x cannot be positive 1. So we have two vertical asymptotes here. We can have as many vertical asymptotes as we possibly want, but in this case it is just 2. Yeah, just 2. So I have x times x minus 1. All right, so there would be our function. So it kind of creates like a quadratic down here. And then it has it going up positive and up positive there. As they get closer to positive 1, where our first asymptote was, and x equals 0, where our other asymptote was. Asymptotes, that's dotted, that's dashed. All right, so they'll be getting closer to those asymptotes as we go out further. Moral of the story. But we can't have multiple. You can have as many asymptotes as you possibly want. All right, with part E, don't get tricked by this up here. It's not really important for finding our vertical asymptotes. Our vertical asymptotes, we only care about the denominator. So x plus 1 times x minus 2 cannot be equal to 0. So x cannot be equal to negative 1. X cannot be equal to 2. That's it. That's our vertical asymptotes. Cool. Yeah. All right. Ooh, we got 3 in this one. Because I have x times 2x plus 3 times x minus 5 cannot be equal to 0. Right, so I have x cannot be equal to 0. 2x plus 3 cannot equal to 0, so subtract 3 divided by 2, so x cannot be negative 3 over 2, and add the 5, so x cannot be 5. So we have 3 vertical asymptotes. Don't get tricked by g here. This 5 on the outside doesn't really do anything, it's just a multiplier. So if I take this cannot be equal to 0, the only ones I have is x cannot be 3, and x cannot be negative 2. I only have 2 asymptotes in that case. Since that 5 doesn't have an x, it doesn't really give us an x value that it doesn't have a 0 for. All right, that's it. Please let me know what questions you guys got as you're going through this, and I look forward to talking. All right, bye.